So in this second part of the presentation, we'll look at the thermal response test, the in situ thermal response test. Originally, it was proposed by Mogensen in 1983, but it took until about 1995, 1996 that the first real mobile tests were developed in the USA and independently in Sweden. Those tests, you can see an example in the little picture on the trailer. Those tests are based on heat injection using an electrical heater. An alternative test was developed in the Netherlands in 1997. It uses a reversible air source heat pump, and it allows you to do a heat extraction and heat injection. The thermal test procedure, the basis of the thermal test procedure is to drill a borehole and install a borehole heat exchanger. Then obviously you need to wait because let's say you've disturbed the underground temperature, you've maybe grouted the borehole and the grout needs to cure. So that will take some time, anywhere between 1 week and a couple of weeks. Then you go back to site, you measure the undisturbed temperature profile, either with the test machine itself or with a temperature probe that you can lower down the heat exchanger, and you connect the test equipment and you start injecting or extracting heat with a constant power rate. This is very important in the standard test protocol, that you have a constant power rate. And you measure the temperature response of the fluid circulating in the borehole. You then analyze the data and calculate the thermal conductivity and the borehole thermal resistance, and if you have the possibilities to do this, the heat capacity. The standard analysis of the data is based on the line source model. You can use other models, analytical or numerical, and those are usually used in combination with a parameter optimization technique. And then if you use a multi-parameter optimization, you can, for instance, also estimate other parameters like the heat capacity. Two examples of test machines. The first one is the standard using an electrical heater. We see a schematic on the left. In the little box 7, we have the borehole heat exchanger, either a single or double U-tube in this case, with the temperature sensors at the top of the borehole. This is important to prevent any influences from, let's say, air or other factors that may affect the measurement itself. We have a connection between the borehole and the test machine indicated by 5. And then in the test machine itself, we have a circulator, a pump at 4. We have electrical heater element at 3. And we've got flow meters at 2 and perhaps a valve to isolate the system when it is being moved around. There's a lot of information in the International Energy Agency ESES Energy Conservation through Energy Storage Annex 21 on thermal response testing. The link is indicated here. And also the German guideline for engineers, the VDI, number 4640, 5. Volume 5 gives information on thermal response testing. Those are all for heat injection only. And in the ideal case, you will have a power control with a solid state relay. The second type of test is based on a reversible air-to-water heat pump. We see a little schematic here of the test with a drawing of how it is being made. It is an air-to-water heat pump that heats up or cools down the buffer tank, and the hot and cold water in the buffer tank, it's always a little bit warmer or a little bit colder than the fluid circulating in the borehole. So we have a storage of potential energy. Using a 3-port valve, we can then control the energy flow to the ground. We also have a circulator, of course, and a flow measurement and temperature measurements with which we can, let's say, monitor the system. It is possible to also integrate a heater with this system and also have power control on the heater with the SSR to allow for higher injection rates or heat injection when it's quite cold outside and the air source heat pump will not be able to provide the capacity. The results, the graph on the top right show you a typical result from a test where you can see that the temperature increases with time. It's a heat injection test, and the rate at which the temperature increases declines with time. So it goes, let's say, to an asymptotic value. And then the central graph shows that if we plot the time as a logarithm of time, and we get a linear relationship. And from that linear relationship, we can, let's say, calculate the angle and the intercept with the axis. We have again a nice formula that tells us that the relationship between the power injection and the thermal conductivity depends on the angle of the graph. You can see the little formula a little bit lower, where it says lambda equals Q, the heat injection rate, divided by 4 times pi times the height of the borehole times the angle of the curve. Once we've calculated the thermal conductivity, we can plug it into the formula together with the measured temperature, and we can calculate with the intercept of the regression equation, we can calculate the actual thermal resistance of the borehole.